Hi, my name's Tracy Haxton. I'm a Technical Director at Wallingford Hydrosolutions, and today I'm going to talk about the FEH Datasets. So we're assuming going into this that you are familiar with the main features of the FEH methods and data, which we do cover in our Introduction to FEH presentation. So FEH, the Flood Estimation Handbook, can be split into supporting literature, datasets and software, and this talk now is going to focus on the datasets, in particular the FEH Webservice and the NRFA peak flow dataset. So as I said, we're going to talk about the NRFA peak flows and the FEH Webservice, and in particular we're going to go into more detail on the BFI Host and urban catchment descriptors. We're also going to talk about the design rainfall. So the NRFA peak flows dataset is managed by the National River Flow Archive, which are part of UKCEH. It was formerly called High Flows UK and is a dataset of approximately 900 gauging stations. For each of these gauging stations there are catchment descriptors, annual maxima and POT data. Predominantly this is used within the statistical method. It's free to download at the following address. So when you download the NRFA peak flows dataset and unzip it, it will be in a number of different folders. Gauging stations are allocated to the correct folder depending on an assessment of their hydrometric quality, so they'll either be not suitable for QMed or pooling, suitable for pooling and suitable for QMed, and these categorizations are used within the WinFAT methodology. For each gauging station there'll be a number of different files, but the ones that we actually need are the CD3 file, which has got the catchment descriptors in, and the AM and PT file, which have got the annual maxima and POT data. So here we've just got a screenshot from WinFAP, so we can see we've got the catchment descriptors here. We can see what the AMAX data might look like, and here we've got the POT data. So we can see there's been set a threshold, and any peaks above that threshold are stored within the POT dataset. So the FEH Webservice is an update from the FEH CD-ROM. All the data that was contained in the CD-ROM is in the FEH Webservice. The FEH Webservice also contains a number of other datasets, primarily the FEH 13 dataset and the BFI Host 19. You can enter from the web, you can create an account and purchase credits. So this is the front end. If we can purchase catchment data or point data, if you purchase a catchment data, you can obtain the FEH 13 or FEH 19 rainfall, as well as all our catchment descriptors, and you can also export the catchment boundaries. For any point, you'll get just the FEH 13 rainfall model, and also the catchment descriptors that you'll need for that point. So this is what it looks like in map form. On the left hand side there's various contextual layers that you can turn on and off. So what I've turned on here are the gauging stations, and these actually have got a link within each one so that it'll take you directly to the NRFA gauging station page. At the bottom there are a list of recently purchased catchments, and you can search for previous catchments as well. So any previous catchments that you've bought will be held in a database. So once you've derived your catchment boundary by doing Alt-click for either your catchment boundary or your point data and bought it, you can then view the catchment descriptors. You can also view the rainfall. So here we've got quite a long list of catchment descriptors, and so I'm going to go into a bit more detail about some of those which are useful. So as I said, there's a large number of catchment descriptors that are exported, but only a much smaller number are used within the estimation methods. So we'll just run over some of those now. So here we've got area, which is the catchment area using the 50 meter IHDTM. We've got the BFI Host, which is the base flow index as estimated using host classes. We've got the DPL bar, which is the average drainage path, and this is related to both the catchment size and the configuration of the river network. DPS bar, which is the mean of the slope, which is a measure of steepness. File, which is an index of flood attenuation to reservoirs and lakes. So a file of 1 indicates there's very little storage and attenuation in a catchment, whereas anything below 0.9 you probably need to look at in more detail. FP extent is the proportion of the catchment in the 100-year floodplain. Prop wet is the proportion of time when the soil moisture deficit was equal or below 6 millimeters for the periods 1961 to 1990, so a sort of signifier of wetness. SAR 61 to 90 is the standard annual average rainfall for the period 61 to 90. Urbex 2000 is the extent of urban and suburban land cover using the LCM 2000. So with the ones I'm going to do in a bit more detail are BFI Host and Urbex 2000. So what is the base flow index? Well, it's the proportion of river runoff which is derived from stored sources. So I've got two extreme examples here. One is the phallic at Glenfalloch, which has got a BFI of 0.16, and the other is the Lambourne at Shore, which has got a BFI of 0.97. So the phallic at Glenfalloch is extremely flashy catchment with a low base flow index, whereas the Lambourne at Shore is a chalky catchment with a lot of groundwater flow within the catchment. IH Report 126 describes how the host dataset has been produced. This is a hydrologically based classification of soils for the United Kingdom. So they took the soil maps, the 1 to 250,000 soil maps, and categorised each of those soil classes into an individual host class, each of which behave hydrologically similar. Then for each 1 kilometre cell, the proportion of host in each of those kilometre cells has been calculated. We can then use a regression equation to calculate the BFI host for any given catchment or cell. Please note that there is a new BFI host equation which was developed in 2019. So here's a map of the host categories, and we can clearly see the chalk outcrops with the clay inside it in the south and East Anglia, and then the more impermeable rocks up in Scotland and Wales and the southwest. So it clearly maps that is very closely linked to both the geology and soils within the UK. So the BFI host estimates are based on these 1 kilometre cells. So if you wanted a point estimate rather than a 1 kilometre average, you can actually look and calculate a localised BFI host value. So we can use the soil descriptors and within the appendix within IH 126 and FEH Book 4, for each soil class it tells us what proportion of each host class is within that soil class. And using the BFI coefficients from IH 126 we can calculate the BFI host. BFI Host 19 was developed to try to rectify some of the issues associated with the original BFI Host model, particularly the tendency to underestimate in dry clay catchments and issues in ephemeral catchments. The latest rainfall runoff model in the FEH 2.3 software also uses BFI Host 19. The model uses a beta model and it uses a far larger dataset than that used within the original development. Here's a link to the online paper where you can find more details. Table 5 of that paper presents the coefficients for the linear models and the linear equivalents as well. Next we're going to talk about urban areas in FEH. So if there is an increase in urban extent, i.e. impervious area, what do we expect to happen in a catchment? Well, we expect there to be a reduction in infiltration and surface storage, therefore increased runoff volumes, and we expect there to be more man-made drainage structures, so a decrease in the catchment response time. Overall, what we're expecting is an increase in peak flows in urban catchments. So it's important to try and reflect the urban land use within a model. At the moment, there are various ways in which we can describe the urban areas. So urban is the mapped urban area, basically the 1 to 50k OS mapped area. Urban 1990 is based on the land cover map from 1990 using the equation represented here. Urbex 2000 is based on land cover map 2000. And you can see that they have different equations and they're derived from different land cover maps and therefore they're not comparable with one another. We can, however, relate ones to the other using some generalized equations. So here's one that relates the urban to the Urbex 2000. So there's some more equations similar to this that are presented in Baylis from 2006. So here we can see in the FEH Webservice the representation of Urbex 1990 and Urbex 2000. So you can see how different they are. Now some of that will be related to how they're calculated, but also the background LCM data as well. It's very useful having these shown in the FEH Webservice because then we can also make amendments for if there's been development post 2000. When we develop our Urbex 2000 estimate, we can then say what type of catchment we've got, and that will determine how we treat that catchment within the FEH methods. So for each category of Urbex 2000, there's a description that goes alongside that. So if it's less than 0.03, we say that it's essentially rural, and if it's greater than 0.6, we say it's extremely heavily urbanized. what we found when we've done research is that in general it's quite difficult to see the impact of urban areas within a catchment where the URBEX 2000 is less than 0.3. Now some impact can definitely be seen in sort of above 0.15 as well. Above 0.3, the urban impact can clearly be seen within regionalized models. So in WinFAT4 and RefH2, they both have similar ways in which the urban is represented. They both use URBEX 2000 by default, so the urban parameters will be based on the URBEX 2000 value if it's given. However, they both also allow catchment-specific modelling, so you can add in areas which have been built up post-2000 if necessary. The general approach is to split the catchment into specific urban and non-urban areas so that a catchment is made up of rural, urban pervious areas and urban impervious areas. Now I'm just going to talk a bit about design rainfall. So as an input to the rainfall runoff method, we require a design rainfall, a given rainfall for a specific return period and duration. So we have what we call the DDF model, the depth, duration, frequency model. So we can see a diagram here from the FEH 99, and so for a specific duration and a specific return period, we can estimate what the rainfall would be for that event. So the FEH 99 model was distributed on the FEH CD-ROM, and it was developed up to a period of 2,000 years. A number of issues were found with the FEH 99, especially as the return periods become larger. So there's significant divergences at 10,000 plus year return periods where the FEH is significantly above FSR, and in some cases the FEH values were even greater than the probable maximum precipitation from FSR. MacDonald and Scott, however, concluded that the problem is probably stemmed from the extrapolation of the line of best fit rather than the statistical analysis itself. So a project was started to look at these long return period rainfalls, and this eventually resulted in the development of the FEH 13 rainfall model. They looked at durations from 1 to 192 hours and return periods from 2 to 10,000 plus years, and they used a dataset which consisted of 6,500 daily rain gauges and almost 1,000 hourly gauges, which is almost double what was used for the FEH 99. The annual maxima were abstracted for 11 key rainfall durations from 1 hour to 8 days, and it was released within the FEH Webservice. And we can see the reference to the original DEFRA report at the bottom. So here's a quick example from FEH 13, FEH 99 ratios. We can see here that there is spatial differences. There are also variations with return periods. Some areas have higher, some areas have lower, and in fact the general picture is that you can't predict for any given location for a particular duration or return period whether the FEH 99 will be higher or lower than the new FEH 13. However, we can come up with some very general patterns. So the FEH 13 estimates tend to be lower and by a greater amount within areas of higher annual rainfall, whereas in drier areas the patterns are more mixed. There is significant local detail, and for example some parts of the Scottish Highlands do show significant increases in depths, even though there is a general pattern of reduction. In general, the spatial patterns do not show a significant dependency on event duration, although this can be seen at the shorter durations. There is a dependency on SAR, and patterns can be seen for long and short durations. As the data used only went down to 1 hour, if FEH 13 data is requested for less than an hour, then the FSR 1 hour to sub-hourly ratio is used to rescale that data. So, which rainfall models should I use? So, in general use, we should use the FEH 13 rainfall where it's available. We should not use the FEH 13 rainfall with RefH1 or the FSR model. Which rainfall model should I use if I'm looking at long-term rainfall, for example, reservoir safety? UKCH recommend using the FEH 13 DDF model to derive the 1 in 10,000 year event. There is no published guidance at present on whether to use the FSR FEH method or the RefH rainfall runoff model. If possible, both models should be used for comparison. A useful comparison of the FSR and FEH 13 rainfall was presented at the joint BHS-BDS meeting last year, March 2019. This found that the rainfall inputs gave similar peak flow estimates when used in RefH2 or the FSR FEH runoff models. However, research into the differences between the runoff models is still ongoing. So I hope that has proved useful. Just as a reminder, here are the main locations of those two datasets, the FEH Webservice and the NRFA peak flow dataset. Thank you.